large domain homomorphic evaluation in leveled mode.
Yeah. Hello, I'm back. Yeah, this works nice. So hello, I'm Jean-Philippe Bossuat, and this is a joint work with Malika Izabachène that will also actually is a sub-work of work I presented before. And yeah. So I will go from an introduction, where this ID comes from. Then I will introduce a general concept about lookup table over large domains, then our proposal, and finally some tables and numbers. So in general, functional bootstrapping allows to evaluate arbitrary functions, which are a priori encoded. But when you try to have high precision, you quickly come into a prohibitive cost. And this talk, we propose a solution that is based on the split domain approach from Ilyashenko et al. That was used to compute private scores over large domains. The premise is that we have a client-server interaction, and the user has a set of private points on which he would like the server to evaluate a private function. And then he retrieves the points by learning the values of the evaluation of this function, but the server learns nothing about the points. So this can be used, for example, like we saw before, to compute a secret score, but also to do heat maps also. Some notations, because we need them. We have a ring of negacyclic polynomials, how we write polynomials. We can also see polynomials as a vector of coefficients. That's the most important notation we have to keep in mind. And then how we note what is an RWE encryption or LWE encryption under some key. So the original split domain approach, the user encrypts his points at the exponent of a monomial, and he wants to retrieve. He wants to retrieve the result as the exponent of the monomial. And to do that, the server does a one-hot encoding of some function from n to n. And we see that if we multiply the one-hot encoding of the message with the matrix of the function, where each row is a one-hot encoding of all the possible values of the function, we get a one-hot encoding of the function evaluation, which actually is just the coefficient representation of the monomial of monomial whose exponent is the evaluation of this function. So given the one-hot encoding of M and the LWE encryption of M and the matrix of F, we should be able to retrieve the encryption of the evaluation of this function. So how to do that is fairly simple. You can see an RWE encryption actually as not a polynomials, but as a matrix, von der Monde matrix, which acts as the same properties than when you collapse it into a negacyclic polynomials. And so you expand this polynomial A into its matrix representation, and then you do a linear operation by multiplying with the matrix. So this still correctly decrypts under the secret key S, but the issue is that now the term A times U is not a valid ciphertext, RWE ciphertext, because the matrix AU is not an anti-circulant von der Monde matrix. So so we talk about split domain. So what do you do if the domain of F is larger than your ring degree? Well, it's very simple. You just discretize the domain of F into multiples of n's, and then you do a function that is a set of an union of function. So you would have one polynomial for each domain of the function. And then to evaluate it, the client will encrypt his message at the exponent of one polynomial, mod n, and all the other polynomials will be, or encryption will be 0, and then the server would just do a dot products between all of these. So we'd have zeros where the index is not in the domain of the function, of the subfunction, and then 1 where it is, and when you sum together, you just get the correct result. Like I said, the result is not a valid RWE ciphertext, and to fix that, they need n switching keys, one for each bit of a secret key, and they do n key switch. This, in a way, homomorphically decrypts back to RWE ciphertext. So for some observation, this approach requires order of n key switchings, n key switching keys. And this comes from the fact that they want to retrieve a result of this evaluation at the exponent, because then it becomes very easy to store all the results into a single polynomial where you add your counts, and in each coefficient you can store how many times this value evaluated to these values f. And this is very efficient because you can store on the order of square root of q counts per coefficient. So the message response is very small. Our proposal is, do we actually need to retrieve the result at the exponent? And what would it change? Because if we don't, we can have a reduced number of key switching operations and also a reduced number of key switching keys. And we'll see what implication if it changes. So the overall idea is to define a test vector polynomial, evaluate it on each point, and then repack the point in a single reduced ciphertext. It's the same approach as this morning, except this time the point is encrypted and not the function. So the first step, the user encrypts his message at the exponent. So similarly to before, if the message has a larger domain than the ring degree, then we just have multiple reduced ciphertext. The server defines a representation of his function to be evaluated, and also if the domain of f is larger than so the advantage of this is that now the domain of f is not limited to the size of the ring degree, since we retrieve the message at the coefficient and not the exponent. And for each ciphertext, now the server just does a polynomial multiplication, and then we can do a sample extraction to retrieve the message. So we get a bunch of reduced ciphertext per point. Now we want to repack them into single reduced ciphertext. We actually get something that is very similar to the original approach, but instead of seeing this reduced ciphertext as a big matrix and a vector, we can see it as a set of structured ring learning error messages that are encrypted under a permutation of the original key. And if we see it as a set of LV samples, then we can actually do combination, addition, and constant multiplication on these LV samples with this matrix that we defined earlier. And we get back a set, not necessarily n, but n or smaller LV samples, which are actually, which is good for us because these are structured ciphertext like we would like to. And this is what enables us to repack them into a single reduced ciphertext, because now we don't have to do this format, key switching format to get back a valid ciphertext. So we can just use the usual ring packing to get back into reduced ciphertext. So ring packing is something that has been worked on before, and essentially it requires one key switching operation per point and only log n keys. So this is quite a big asymptotic improvement over the original approach, because we now need only O1 of key switching key per point, key switching operation per point, and in a total of log n key only. But now we have to see what it implies on the query size, the message response, and the computation. So the query size remains the same because the encoding is exactly the same. We encrypt the message at the exponent. So it has a size that is proportional to the domain of the function times what it would take in number of bits to encrypt its message. And now what is the main difference is the response. So the response is now proportional to the number of points and not anymore to the domain of the message, of the image of f. The reason is that since we don't have m at the exponent anymore, the image of the function is not constrained to the ring degree, but we can store at most n points per polynomials. So our approach is better when the domain and the image of h are large, but it's worse when you have a lot of points. However, it still remains better when the image of f is large, because then, since the response of the original work has a response that is proportional to the image of f, because the image of f is constrained by the ring degree. If your image of f is large, then you can still the answer does not depend on the image of f because you store it in the coefficient. So this is a summary with tables of the comparisons. So we can see that the query size is the same because we encoded the same, and then the number of keys is asymptotically better as well as the evaluation, and the response size now is proportional to the number of points and not anymore to the size of the image of f. So concretely, what does this give us? We implemented our solution with Lattigo, and the code is available again at the same repository. So we did the experiments trying to use the same parameters and function domain and input than the original work. And essentially what the original work was reporting is the evaluation. So the encryption and query size remain the same, and what matters now is the evaluation. And we did it for a batch of 2048 points because we used the ring degree of 2 to the 12, which was in the original work. And we can see that this approach, for a batch of 2048 points, is about 2,000 times more efficient. We did the same for the multivariate approach, where you compose two functions linearly. And again, it's close to 2,000 times. And the response size remains also very acceptable, same as the key that's only like a few megabytes. We can see that the encryption and the query size are quite big. And this is something that could be tackled further because compressing this value could help a lot in single polynomials. And like in the first talk this morning, by doing the opposite, encrypting the function and not the points, we can save up a lot of this because the function has a fixed size. And then the points, all you need is to one-hand encode them. But it changed the adversarial model. So we have to keep that in mind. And yeah, this has the references. So voilà, thank you.
Thank you for a nice presentation. Questions? Yes. Oh, over there.
Yes, thank you for another nice presentation. Yes, I have another question with performance. So how parallelizable is implementation? So are the numbers you mentioned for a single thread?
Yes, everything for a single thread. So it's embarrassingly parallelizable. Yes, you could easily parallelize it. At every step, even the ring packing can be parallelized.
Great, thanks.
More questions? Wants a question? If not, let's thank the speaker again. It's not going to disappear. Thank you.